Welcome back to the deep dive. Today we're tackling what you could call the holy grail of modern physics.
It really is. We're talking about unifying general relativity, the physics of the very, very large, and quantum mechanics, the very strange physics of the small.
And for decades, these two ideas have been, well, brilliant, but totally incompatible.
Completely. They just don't speak the same mathematical language.
Okay, so the sources we've gathered for this deep dive propose, I'd say, a pretty radical solution. It's a framework called the Fractal Spacetime Hypothesis, or FST.
Right. And our mission today is to really unpack how this idea uses geometry, specifically the geometry of roughness, of repeating patterns, to finally maybe bridge that gap.
What I find so fascinating is that it all starts with a very, very old philosophical idea.
It does. FST is basically the mathematical formalization of the Hermetic axiom. As above, so below.
Which comes from the Emerald Tablet, right? This idea that the patterns you see in the macrocosm out in space, they repeat themselves in the microcosm down at the quantum level.
Exactly. Like, the universe is a kind of cosmic Russian nesting doll.
Yeah.
And this isn't just a nice philosophical thought. We actually have observational evidence for it.
Oh, okay. So this isn't just a theory. There's data to back up the core concept.
There is. Look at black hole accretion physics. You have stellar black holes, maybe 10 times the sun's mass, and then you have supermassive ones, billions of times the sun's mass.
So wildly different scale.
Wildly different.
Yeah.
But observations show they have this mass invariant behavior. When they consume matter, they do it in almost the exact same way.
Wait, you mean a little black hole like V404 SIG looks the same physically as a monster like M81?
Fundamentally, yes. The physics scales perfectly over 8 orders of magnitude in mass. It's not about their absolute size, it's about their relative accretion rate. The patterns are self-similar. It's like the cosmos is screaming at us that this principle is built into its very fabric.
That sets the stage perfectly then for the core idea of the whole theory, the fractal. Most people think of, pretty computer images. But what's the actual mathematical definition we need here?
Well, a fractal, as Benoit Mandelbrot defined it, is a geometric shape that has detailed structure at arbitrarily small scales. You can keep zooming in, and you never reach a smooth bottom level.
Like the classic Cox snowflake example. You zoom in on the edge, and you just see the same jagged pattern again and again.
And again. So that's the first key idea. Self-similarity. You see it in nature, too, like Romanesco broccoli or the branching in our own blood vessels.
But there's a second characteristic, right? The mathematical part.
Yeah, and this is the kicker. A true fractal has a fractal dimension that is strictly greater than its topological dimension.
Okay, bring that down.
A simple line has a dimension of 1, but a fractal line, like the edge of that snowflake, is so infinitely jagged and crinkled that it starts to fill up space more than a simple line should. Its fractal dimension might be something like 1.26. It's the math of roughness.
It fills more space than it should. I like that. So, what happens when you apply that idea, that roughness, to the fabric of space-time itself?
This is where the FST hypothesis makes its big move. It says that space-time is not smooth and continuous, which is a core assumption of Einstein's. That smoothness is just an illusion of scale.
An illusion we see at our large, low-energy level.
Precisely. But if you could zoom in, way down to the Planck scale, where quantum effects take over,
then space-time gets rough.
It gets rough. It becomes a self-similar fractal structure. Some physicists call it quantum foam. And this is where the most important variable of the whole theory comes in, the fractal dimension, which we call dollars.
And this variable, it's not a constant number.
No, and this is crucial. It's scale dependent. Its value changes depending on how closely you're looking.
Okay, so physically, what is dollars telling us?
At our large scale, the dollars is basically 4. 3 dimensions of space, 1 of time. That's the smooth world Einstein described. But as you probe smaller and smaller scales at higher and higher energies, dollars starts to deviate from 4.
It deviates how?
The models suggest it might drop, maybe towards 2. Space-time would locally behave more like a surface than a volume, and that would, well, it would drastically change how forces and particles behave down there.
A drop in dimension. That's a profound thought. So the deviation of dollars from 4 to 2, that's the signal. That's the mathematical proof that the geometry has changed.
That's the bridge. That's the entire unifying mechanism. Because if the geometry of space-time changes when you zoom in, then general relativity, which is built on smooth space-time,
has to be wrong, or at least incomplete.
Incomplete, exactly. Which means we have to modify its master equation.
Einstein's field equations, which, in the simplest terms, say that the curvature of spacetime on one side of the equation is proportional to the mass and energy on the other side.
Yeah, but a fractal spacetime needs a new equation. So we introduce a fractal spacetime metric, and that leads to a modified version of the field equations.
And looking at it, there's a new term in there. There's the usual cosmological constant, lambda, but now there's the fractal correction tensor.
The new kid on the block. And that's the term that accounts for all of this. It's the mathematical expression of that geometric roughness.
So it's not just some patch you add on, it represents the actual stress that gravity feels because the space it's moving through is no longer smooth.
That's a perfect way to put it. We can actually interpret a mu nu as a new source of gravity, a source that doesn't come from mass, but arises directly from the self-similar patterns of space-time itself.
And if you make that change to gravity, it has huge implications for the big cosmic mysteries, dark matter and dark energy.
It offers explanations that are based on geometry, not on some new exotic particle we can't seem to find.
So for dark matter, how does a folded geometry look like mass?
Well, think of it like this. If space is folded fractally, there are these hidden, higher dimensional creases. Matter traveling through that space feels the gravitational pull of those folds.
So we see the gravity, but because the source is purely geometric, it doesn't interact with light, it stays invisible.
It's electromagnetically invisible. It exerts gravity, but it doesn't shine. Which is a much more, I'd say, elegant solution than inventing a particle that just happens to avoid all our detectors.
And dark energy, the force accelerating the expansion of the universe.
That goes back to the scale dependence of dollars. At vast cosmic distances, the fractal geometry could actually modify the force of gravity itself, causing it to push instead of pull, leading to that accelerated expansion. It could solve the whole cosmological constant problem dynamically.
It's all connected. The microscopic roughness is structurally linked to the cosmic scale behavior.
Okay, let's flip the coin. How does this affect the quantum world?
In the exact same way. Just as it modifies GR on the macro scale, it has to generalize quantum mechanics on the micro scale. The particles are moving through a rough environment now.
So their wave function has to be updated to account for that.
Right. We move from the standard Schrödinger equation to a new generalized one. And just like with gravity, there's a new term.
Let me guess. A fractal potential? You got it. The fractal potential, UFX DAW. This potential represents a brand new type of interaction. It's a genuine quantum gravity effect, the interaction between a particle and the fractal geometry it's embedded in.
So the fractal spacetime itself creates this invisible field that influences particles. It's the information carrier between the geometry and the quantum realm.
Yes. And this framework gives us powerful new ways to think about classic quantum paradoxes, like entanglement.
Spooky action at a distance. How does FST explain it?
This is where it really shines. FST says entanglement is natural because particles are never truly separate. Even across the universe, they're linked through this intricate web of fractal connections.
So the non-local correlation isn't spooky. It's just communication through the shared geometry they both exist in.
They're reading from the same geometric source code. The geometry itself encodes those correlations.
What about superposition? A particle being in multiple states at once?
That finds a natural home in the fractal geometry. The overlapping cycles and self-similar patterns provide a structure where different, even conflicting states can coexist.
And wave function collapse when we measure it and it snaps to one state.
FST views that as the measurement forcing an interaction between the particle and the fractal geometry. The system is forced to couple to one specific fractal path, and that's the state we measure.
The theory also seems to generalize Heisenberg's uncertainty principle.
It does. The fractal dimension dollar introduces enhanced quantum fluctuations, which get stronger and stronger as you approach the Planck length, around 1035 meters. This is the scale where we expect quantum gravity to take over, and FST predicts measurable effects right at that boundary.
Which brings us to the most important question for any theory. How do you test it?
FST makes several distinct testable predictions, which is what makes it so compelling.
So we can go beyond speculation.
Absolutely. One way is through high-energy particle collisions, like at the LHC. We look for tiny deviations from what the standard model predicts.
What kind of deviations exactly?
You might see energy appearing to leak out of our four dimensions into those hidden geometric creases. So you look for missing energy in the collision debris, or maybe even new particles that are purely geometric in origin.
So that's probing the small scale. What about the large scale?
For that, we turn to astrophysics. We can analyze the light from gamma ray bursts that has traveled for billions of years. If spacetime is even slightly fractal, that journey would subtly alter the light. We could look for tiny signatures in the spectra.
And you mentioned something about telescope experiments.
Yes, this is really exciting.
Yes.
Using atom interferometry, which is incredibly precise, you can measure the free fall acceleration of atoms. FST predicts that the pull of gravity would be slightly different than what smooth GR says it should be.
You could find the fractal signature of the universe on a lab bench.
You could. And finally, with gravitational waves, the theory predicts that merging black holes would have slightly different dynamics. The ring down, the sound the new black hole makes as it settles, would have a different frequency than what Einstein predicts.
These are real, concrete places where the theory meets reality.
Exactly.
So, bringing it all together, we started with this ancient axiom, as above, so below. This FST model really seems to suggest a deep convergence between science and that philosophy.
It does. It suggests the universe runs on a self-referencing, self-similar code. That all the complexity we see arises from the endless repetition of a simple geometric rule. The microcosm really does reflect the macrocosm.
And if we're embedded in that reality,
Yeah.
what does that say about us, about consciousness?
Well, the sources suggest it blurs the line between the observer and the observed. It hints that our own consciousness might be a local reflection of these larger cosmic patterns.
Meaning that if you truly understand the smallest piece of reality, that jagged quantum foam, you inherently understand the blueprint for the entire cosmos.
Because they share the same geometric DNA.
That is a staggering thought. So to recap, the core achievement here is the scale-dependent fractal dimension, dollars. It modifies gravity with a fractal correction tensor, and it generalizes quantum mechanics with the fractal potential, UFX.
And by doing that, it provides a single, unified framework that is both mathematically beautiful and crucially empirically testable.
So here's the final thought for you to carry with you. If every fragment of our world, no matter how modest, a neuron firing in your brain, a coastline, a ripple in space-time, if it all fractally reflects the entire tapestry of the universe, what does that imply about your own observations? If the macro is truly in the micro, what profound truth about the whole cosmos could you unlock just by deeply studying the patterns right in front of you?
That is definitely something to muse on. Thank you for joining us for this deep dive.
We'll see you next time.